All right, in this video, we'll look at problem 4, which is asking us to compute the line integral of the vector field f, where f is xi plus yj plus xyk over the curve C, where C is the portion of the helix given by this vector function r of t, which is cos ti plus sine tj plus tk, and we're letting t vary from 0 to pi. Okay, so this is a picture here of this portion of the helix we're going to integrate over, and here are the vector function describing C and our vector field. Okay, so now recall from the last video, to compute a vector line integral like this, we are going to compute the integral of our vector field f restricted to our path, so f of r of t, and then we're going to be dotting that with the derivative vector r prime, and we're integrating here with respect to t, and here t varies from 0 to pi. Okay, so we derived this expression in the last video. All right, so now how about this part, f of r of t? Well, if this is f, and this is our r of t that describes the path C, f of r of t would then just be the vector where I'm just going to substitute in cosine t for x, sine t for y, and t for z. And notice I don't actually see any z in there, but in any event, I'm going to get what? I'm going to get cosine ti plus sine tj plus x times y, that'd be cos t sine t k. All right, so that part's going to go right in here. Now, what's r prime? Do this right here. R prime, this is going to be minus sine ti plus cos tj plus just k. So I'm just differentiating these component functions with respect to t to get r prime. Okay, so now let's punch all of those in. So I'm going to be integrating from 0 to pi. First, I'll put in the f of r of t, so that's cos ti plus sine tj plus this product cos t sine t k. And then we're going to dot that with this vector here in blue, which is r prime. So this is minus sine ti plus cosine tj plus k. Okay, and then we're integrating with respect to t. Okay, now when you compute this dot product, this feels like just kind of a horrible mess, but actually it's not too bad, because what am I going to get? I'm going to get cosine t times minus sine t. So that's going to be minus cos t sine t. Then I'm going to get plus sine t times cosine t. Oh, okay, that's nice. These are just going to cancel out. And then lastly, I'm going to get cos t sine t times just 1. And so that's just going to give us a cos t sine t. And now we're in pretty good shape, because these are going to drop out. And so we're looking at the integral from 0 to pi of cos t sine t. Now you could use substitution here, that'd be fine. Maybe let u equal sine or cosine if you like. Or you could also use double angle identity. This is half of sine of 2t. Okay, so I'll go ahead and do the substitution. You're going to get 1/2 sine squared t. We're evaluating from 0 to pi. and putting pi in, you're going to get 0, putting 0 in, you're going to get 0. So in fact, this comes out to be 0. Okay. So based on our discussion from the last video, does that mean that our vector field, say, always points orthogonal to our path to get a line integral of 0? No, it certainly does not. And we can even see that that's not the case because I know that my vector field f here dotted with the velocity vector is not equal to 0. Okay, so our vector field does not always point orthogonal. Okay, but remember this line integral is giving us an overall measure of the tangential contribution from this vector field f as we move along the path c. So the fact that this does come out to be 0 just is saying that you're going to have, well, some positive contribution, meaning some of the force vectors will point in the direction of motion, but then you're also going to have, right, some contribution that will be negative, meaning that the force vectors will point in the direction against motion. And in fact, since this integral is 0, right, those contributions will be equal and opposite. Okay, so that'll do it for this one, and I'll see you in the next video.